and then show you how it operates. So the first thing that's in it is a coil. So there's several turns of a wiring material here. There's a small RF amplifier that takes a DC input and oscillates it, in this case at 250 kilohertz. So it creates what we call a high-frequency oscillating magnetic field. By the way, cell phone guys don't consider 250 kilohertz high frequency. But compared to the wall power, it's pretty high frequency. And then what we do is you can place in the back of the cell phone a coil and electronics. Now, one thing you'll see when I demonstrate this to you, think of a transformer in sort of classic inductive sense. These are not the same size. They won't be oriented the same way. And what I wanted to do was go for position independence. So you still have to plug it in. I'll get to that in sort of my last demonstration. So I'll just use a rechargeable battery here. That's sufficient to power it up. So now I basically plugged in DC input, 5 volts. I'm creating an oscillating magnetic field. And you'll see when I put the cell phone up here, see how the cell phone just came on? Actually, it's probably, because there's a time constant on the display, but there's a little green light. If you can see it there, I'm not sure if you can. Oh, yeah. Look, so you see, first of all, when I put it up here, I didn't care where I put it. I wasn't thinking about it. So right away, it offers utility to the consumer. But what's really cool about this is, look how far away it was. That green light is still on. Probably when I get them another centimeter or two away, it'll stop. It's still on. There, he stopped right there and flips back to the battery. So he works sort of out there. By the way, he works next to it. Those of you that want, need to work through my head. And one thing that's worth sort of mentioning, people ask is it safe, right? That's sort of the question people ask. So it turns out the math, when you do the math, doing what I just did is 100 times safer than making a cell phone call. Now, I don't think I'd say that to the cell phone. I don't think I'd say that to the cell phone companies. You're probably going to put it up. Because cell phones, as I think most of us know, are very safe. This is a couple orders of magnitude safer than that. Now, one of the things that's really neat about that, you might say, why does it matter that you can charge at a distance? Well, one of the reasons you might want to do that, see if I can demonstrate this actually. We're not going to be able to look on the top of the table. Maybe if I just do this, right? So imagine the thing's underneath the table. Just sort of under here like this. Pardon? See how the green light's on there? You know what? I have an easier way to demonstrate this. I just thought about it. Let's use light. Okay? So a lot of people will almost inevitably ask, what does the math look like that determines the efficiency, how far can you go, and those sorts of things? So the efficiency curve and the energy transfer is defined by the math. And let me give you the math. It's the product of the surface areas of the resonant objects. So this is a resonant object, this is a resonant object. This one, assume that the coil or the resonator in here is around the diameter of the light. So that's pi r squared, if I remember my basic area, right, my geometry, whatever. And this one's got an x times y. So if you take the x times y of this and multiply it times the pi r squared here, you get a number. That number determines the efficiency. And you'll see that you notice that I didn't really care sort of where it is because it's in the field. I mean, it works at a right angle. It works, as I said, at a distance. And if you wanted to look at the efficiency curve that generates, the curve is kind of a flat curve before it falls off exponentially. So look how far away. But you see in that space here, the curve is flat. And that's generally the part of the curve that we like to use for getting this phenomena to operate efficiently. And that generally is, once you get past this point, it's dropping off to, 1 over r cubed, so it falls off exponentially, and just, the energy is not terrifically useful. Now, one of the things that's also interesting about the technology is, it's probably hard to do this here, but let's see if I can. So the cell phone's on. I'm guessing I could probably get the light here on somehow. Yeah, so you'll see it works with multiple objects as well. So if you think about the efficiency, let's assume for a moment that you wanted to power 2 cell phones. So you've designed your system to actually only be 50% efficient to one. When you bring the other object up, that other 50%, usually people forget to ask you, what happens to the other 50%? This is not radiated. It doesn't go off into space like the cell phone. It actually is available for use by any other device. So you could design one of these things that's 20% efficient, and you could have 5 devices, each picking up 20%, thereby approaching sort of 100% efficiency. So it's one thing to keep it in mind when you do that. I wanted to show you sort of one other really wild parts of this phenomenon. Because usually people will say, hey, can you go farther? I'd like to go farther. Well, remember I said it's surface area based. So we go back to sort of the cell phone, or let's use the light actually. So you see how he stopped working here? So that sort of defines when it stopped working. And you can create objects that are resonant, that are completely passive. Can I get somebody just from the audience, or maybe somebody could just come out there for a minute? Just sort of help me a second. So if you want to just hold the light up there. So you see how that stops, now start to move them slowly that way. Keep moving, keep moving, keep moving, keep moving, keep moving. See how he stops? But if we put another object in there that's resonant, we're actually hopping. So we're using a repeater. And actually, the repeater phenomenon, it works, to bring your hand up higher. So you can actually go all the way across rooms this way. And if I drew the code for you, it exists actually. If you can create the right section of intersection curves, we've been able to do this in our offices back in Boston, where what we've done is place passive resonators in carpet. So it's in individual carpet piles, and you can light lights anywhere in the room based on a coil that sits in a switchblade that's only probably that big. So we're able to break the distance barrier by using passive objects. The size of these things, by the way, this is actually one that puts out 2.5 watts. It's designed to be about the size of a cell phone battery. Eventually it will incorporate the cell phone battery, the coil, the electronics. But this one just outputs 5 volts DC. If somebody, if they have one of these USB things, is welcome to try it after we're done, see if you can charge your cell phone wirelessly. So I'd like to take you sort of further up the power curve now, if I could. So let's probably just take this off here. I want to go back to the electric car. So this is, I couldn't bring an electric car in and put it up on the stage here, so I'm going to have to satisfy our curiosity with some lights, okay? So just, I want to lay this out for you here. Those are 2 500-watt halogen bulbs. You'll see there's a wire coming to a coil or a resonator. Assume this one's bolted underneath your car. It's shielded and designed to actually sit underneath the car. So we started shipping these from auto companies. And there's a similar object here. You saw with the alignment, I can change it. And so that's one of the other benefits of putting this on an electric car is that you can do a lousy job of parking your car and actually have it continue to have the same efficiency. And imagine that the one that's here is on the floor of your garage or under the cement like I showed you through the table. And what you do is you have something plugged into the wall. And I put a meter on this, so I just want to make sure I explain what we're looking at here. So I've got a DC supply. This is an off-the-shelf power supply. Those of you that remember your power electronics, right? Voltage times current. So you'll be able to see the display. here to see the actual input power. And it goes to an RF amplifier. This was working at 145 kilohertz. It works really well in the automotive environment. So it'll go in, create a field, create another one there that will go to the lights. And so you'll see it's putting about, 225 volts, 3.3 amps. I don't know how bright you think that is, but that looks like almost 1,000 watts. I assure you it's not 1,000 watts. It's 96% of that number. So anybody with a quick calculator, 225 volts times 3.3, what, about 800 watts, something like that? It's on that order. So you're looking, that looks to me like 800 watts. And the reason is, this is 96% efficient between these coils. So you're looking at something that if you were in transformer land, or thinking about transformers, that distance is infinity. The transformer would have long ago stopped working. So it's sort of this 20 centimeter distance. That's well above the ground clearance of any electric car that's on the market now. And we're able to actually do this quite efficiently. The other thing to point out is the magnetic field. By the time I'm 1 coil diameter away, it's virtually impossible to find the field. It still exists. And the electric fields are tiny, because the electric fields actually only exist around the conductors inside the resonator itself. I wanted to give it one more thought as we think about, could I get the distance to go even farther? So, this one I've never tried live before, so we'll see if it works or not. But how about going 149 million kilometers, right? That's the sun, solar, right? So here's a solar panel. It's a traditional solar panel, and it's not, it's no longer daylight out there. But we've actually started doing installations of these. You can place them on roofs of buildings where you put the resonator and the amplifier directly on behind the solar panel, then you just throw it up on the roof. You go inside the house, sort of like I showed you at the table, stick another resonator inside the house and go back to your house wiring, and you can get, eliminate half the cost of solar installations, because the installation is a very expensive part. So you don't have to put holes through the roof and things like that, which will cause moisture to get in. You don't need specialized labor to put up solar installations. What I'd like to do is just sort of show you it working here if I can. So I'll just run the output of the solar panel. I may need somebody to help me. Somebody can, I probably can't do this for myself. We'll just pretend those lights are the sun, right? So, just a second. And if you want to just go hold them up there against the other way. Yeah, so you'll see, so that's free energy, right? If that were the sunshine, you'd be looking at So, I think that's pretty much it. I have one more slide, which I always like to end with, and then take a few questions. It came out of the New Yorker magazine. See the guy sitting up in